Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. I think we stopped here last time when we were talking about the margin of a data set. We were talking about the context of convergence, okay? And we mentioned that Perceptron will never converge if the data set is not linearly separable, okay? And then we started to talk about the condition for the number of, for how long actually the perceptron will take before convergence, okay? And to do that, we started by defining what we called the margin of the data set. We started by defining the margin of a model first, right? And we defined it as the distance between the model and the closest point, right? So for example here, the margin of H2 is this distance, okay, because this point is the closest to it. The margin for H3 is that distance, okay? We don't care about H1 because H1 actually is not separating the space between the positive and negative examples here. It was just an example of non-separating hyperplane or a line. And then we related this concept of a margin of a model to how good the model is, right? If the margin of the model with respect to this specific data set is very small, what does that mean? And in this case, H2, the margin of H2 is very small, right? Should we care about that? Does that have any meaning? Will be what? Bad. Will be bad. Bad in terms of what? Why is it bad? Why is it bad? Nayyam?
Because we have examples that closer to the black set, then, and the H2 will classify it as white. But
Yes.
it's not white.
Yeah, because if the margin is very small, that means that it is very close to one of the regions, right? Or the positive or negative region, which means that it might not generalize well in the future. Okay, generalize well means that it will work well in reality or in the future with unseen data. Okay, getting close, very close to one of the sides, that might lead to mistakes in the future, right? Because as you said, if there is a point here which is really close to the black points, it will be considered white, right? That's because the model itself is not generalized, it doesn't generalize well to the unseen data. If we look at H3, we'll see that the margin is much larger, which means that it is on a safe side. It will, most probably it will generalize much better than H2. Okay? Is that clear? Right. We can also generalize that to the data set. So if we know the margins of the models, then the margin of a data set is the largest margin possible for any of the models. Okay? So as we said last time, if we have all the models here, it seems like H3 will be the one that has the largest margin, and thus that margin will be the margin of the data set. Okay? Right. Now, what is the meaning of the margin of a data set? If that margin is very large, what does that mean? And if that margin is very small, what does that mean? Yes?
If the margin is very large, that means that the data are separated, not close to each other, maybe.
Right. Let me clarify one thing here. When we talk about a margin of a data set, we assume already that the data set is linearly separable. So the data set is already separable. Okay? That's by definition. Yani we don't have a definition for a margin of a data set that is not linearly separable. Okay? So we assume that the data set is already separable. So if the margin of that data set is very small, what does that mean geometrically? Yani let's look at it geometrically. Okay? how that will look like, how that data set will look like. It is already separable, right? It is linearly separable, which means that we can find a hyperplane that will separate the positive and the negative region. Okay? Type. Now, when the margin is very small, that means that these two regions are very close to each other, right? If the margin is very small, then it is like when we push these white points to that direction. Okay? It will come very close to the black points. Still, they are separable, but the margin is very small. Because whenever we find a model that will separate these two, the distance between that model and the closest point will be small. Okay? Type. What is the implication of that? If that area that separates these two regions is very small area, what is the implication of that? Yes?
The probability of making mistakes become higher.
Okay, which I can also say that from that means that it will be harder to find the hyperplane that will separate them. Okay, it will take much more time because it will, as you said, it will make more mistakes. It will take much more time to converge. It will take much more time to find the model that will separate both regions because the area is very small. If the area is very large, then there are many, right? Now, if it is very small, the number of possible models that will separate both will be small, right? But if the area is large, then there are so many models. Yani هنا, in this case, we can find a model like that, we can find a model like that, right? We can find a model like that. There are so many models, much more than if the margin is small. Okay, and thus finding one of them will be much faster, right? Easier and thus faster to find relative to the other case when the margin is very small. Is that point clear? Okay, so this will now relate the margin of the data set with how fast we can find a model that will separate the positive and negative examples, or how slow. Okay, any question about this? Right. Now let's discuss a theory about the convergence. It's called Perceptron Convergence theorem. It was proved in 1958, so it's a really old theory. What it says is that it will give us an upper bound of how many updates the model can go through before it converges. Okay, so the theory says that if we have a linearly separable data set, so we start with a data set that is already linearly separable, so we can find a separator for it, or a good model for it, and that data set has a margin of gamma. So the data set has a margin gamma. Then we assume that all the points in that data set, the length of every example in that data set is less than 1. If not, of course, we can normalize it. Then, in this case, the algorithm will converge after at most 1 over gamma square updates. What does that mean? First, what is the meaning of convergence? We talked about convergence last time, right? What is the meaning of convergence in the context of perceptron? It finds, yes, so the algorithm finds a hyperplane that separates both sides, right? Which means that it will not make any mistakes if we predict the labels for the training data. Okay, so that's the meaning of convergence. The model is stable. Alas, we will not need to update the model anymore because it will not make any mistakes on the training data. So it converges. Right. Now the theory is talking about when can that happen. The theory says that if the margin is gamma, then after at most maximum of 1 over gamma square, of course gamma here is less than 1, after at most 1 over gamma square updates, the model will converge. Type. what do we mean by updates? When do we update the model in Perceptron? When it makes a mistake, right? So that means that after 1 over gamma square mistakes, maximum, the model will converge. That's the theory, and there is a proof, of course, in the textbook. Type. What does that mean? It means that the number of errors that the algorithm or the model that will make, maximum will be 1 over gamma square. Type. If gamma is the margin of the data set. If the margin is large, we said that it will be easier to find the model, right? That will be easier for convergence, right? That means the easier means faster, which means that it will need less number of updates, right? Let's look at the theory and see if it really matches this or not. If gamma is large, gamma square is also large, right? Like 1 over a large number, small. So the number of updates will be really small before the model will converge, which means that the model will converge fast. Okay? If gamma is small, then of course gamma square is small, very small, and thus 1 over gamma square will be very large. That means that the number of updates is bigger. So it will take more time to converge. So when the margin is large, it will be fast or slow? Think about it geometrically. If the margin is large, then the positive and negative examples are far from each other. So the convergence will be fast or slow? Fast, because there are many models that will separate, right? Finding one of them will be fast. If the margin is very small, then it will be hard, which means that it will take more time. It will be slow. Okay, so that's what this theory is telling us. So perceptron will converge quickly when the margin is large, slowly when it is small. Type. The second point, look at the theory here. This is the upper bound of the updates, right? The upper bound of the mistakes before convergence. Does it depend on the number of examples? It doesn't, right? It just depends on the margin, right? It doesn't depend on the number of examples. Type. Does it depend on the number of features that we have? No. And this is good. Okay? If we have so many examples or so many features, that will not make the conversions slower or faster. Okay? It depends on the margin of the data set. It depends on how far the positive and negative examples from each other. Okay? Not how many features, not how many examples. Okay? So that's the second point here. Bound doesn't depend on the number of training examples nor the number of features. Do you understand this point? Okay, the last one, which I think we discussed last time, if I remember. This theory doesn't tell us that the model that we will converge to is the best model, is the one that is maximum margin separator. What do you mean by maximum margin separator? The one that has the largest margin. Okay? You know, and even if the data has very large margin, I might have very bad model like that, right? Still, it is a separator, right? But it's not a maximum margin separator. Maximum margin separator means it has a maximum margin. What is the one that here it has the maximum margin? The red one, H3, right? But something like this is possible. And it can converge to this, right? It is still separating. It has very small margin, but it is separating, right? The theory doesn't tell us that we will find H3. It said that it will converge with maximum of 1 over gamma squared. Converge to what? It will converge to something that will separate them, but it doesn't guarantee that it will converge to the best. It will converge to the maximum margin separator. Okay? Is that clear? Okay, so that's the third point here. That proving this theorem doesn't guarantee that the perceptron guarantees that perceptron will converge, but not necessarily to the maximum margin separator. It will converge. That's guaranteed. It will converge. Maximum after maximum of 1 over gamma square updates or mistakes, but it might not converge to the maximum separator, maximum margin separator. Okay. Type. What if the data is not linearly separable due to some noise? If we have this data and for some reason we got a white point here, it's like a noise, right? What will happen? This is not linearly separable. So we will never converge. The model will never converge. Okay? Will never converge. Type. So that's a limitation, of course, for Perceptron. Another limitation is that there are some simple data sets that are not linearly separable or linearly inseparable, like the one that you see here. This is called the XOR problem. We have 2 points, 2 dark points, and 2 light points, like that. Will we be able to find the hyperplane? Can we separate the positive from negative examples here? No way. Although it's just 4 points. Even with this, there's no way to separate them also by a line. This is called the XOR problem. You remember XOR gate in Boolean algebra? Okay. When one of the 2 features or the 2 variables is 1, it is 1. And if none or both are zeros, if both are the same, then the value is 0. Okay, there is no way to separate these 2 by a line. Okay, there's no way to separate them by a line. And that simple problem and the failure of Perceptron to provide a solution for it blocked the entire field for long years. Okay, because it was not able to actually solve this simple problem. Of course, later the community managed to overcome this problem, and we'll see, inshallah, in this course at least 1 solution and maybe 2 if we have time, inshallah. One of these solutions actually is the idea of adding features. Okay, so we have training examples with some features. We can add combinations of these features as additional features. How this will be useful? Let me show you an example. This is example of a data that just has 1 feature only. Okay, some of the examples are blue and some are red, positive and negative. Can we find a line that separates them? No way. It's just 1 feature, by the way. 1 feature only. So this data set is just 1 feature. But it is not linearly separable. So Perceptron will never be able to converge here. But some nonlinear solution like the green one is separating them, right? But Perceptron cannot. Let's see if we do some transformation to this, what will happen. What we will do now is to add a new feature. Okay, we'll call the first feature x, which is the value here on this axis. And the other features that we will add will be x squared. We'll just square the same feature and add it as a second feature. So now how many features we have? 2, x and x squared. Just 2 features. Let's see what will happen now when we do this. When we do that, the blue dots here, the blue examples here, are still blue here. But now they are in 2 dimensions, not just 1. Okay, and guess what now? We will be able to separate them using Perceptron. Okay, you see now, the red points are still the red points here. And the blue points are still the blue points here. The only difference is that we added a new feature, which is x squared. Now, when we added this new feature, we have a new space. In that new space, the data set is linearly separable. But in the original space, it's not. So what is the idea here? The idea here is that we can do transformation to the data set that will make it linearly separable, although it is originally not linearly separable. Yes?
I don't get this.
Okay, you didn't get what? The whole issue here?
The shift of the points.
Okay,
Correct points.
okay. Okay, let's say that this is 0. Okay? It's one feature, right? So it's either positive or negative. It's just the one value. So this is positive, and this is negative. Okay? Right. We added a new value, which is a new feature, which is x squared. So let's plot these new features. It's the same examples, but we added one feature in each example. So now this point, where will it be? It will be x and x squared, right? Right? So this point, actually, it will be now this point. It will have positive value in x, because it's positive already, and square of that value in x squared, because it's x squared, right? So we actually squared that value. So now it will be in this point. This one will be that point. This one will be mapped to that point. This one will be mapped to this one, and so on. So all of these and this one probably will be this one. Okay, in the new space. This is the original space. This is the new space. This is 1 dimensions, right? This is 2 dimensions. And we do the same for the red ones, of course. Okay, so for example, this one is this one. Okay, x is the same value. In x, if you get the x value, it is the same, but we added x squared also. When we added x squared, the values that are large positive or large negative, it became all large positive because we squared, right? So the square of positive and square and negative are both positive, right? So they will have large values. Now they will be on top of the blue ones. So we can now separate them. Okay? Of course, it's easy to see it after we do it. Okay? But the idea itself is not easy to get. Okay? But I hope that you understand the idea, right? So adding features might convert the data set from a non-linear, linearly inseparable data to linearly separable data. Okay? We call this either transformation or feature combination or feature mapping. Type. What is the problem with that? The problem with that is it's not easy to find such combinations. Maybe with one feature, okay, we can think of maybe multiplying the feature by a scalar or squaring or maybe cubing or something like that. What if we have 10 features? Which features we should combine together? And what is the transformation exactly? What if we have 100 features? What if we have millions of features? Okay? That will not scale. So it's not easy to find an efficient way for this transformation. So inshallah, in the maybe second half of the course, we'll see two approaches for that. First, we will combine multiple perceptrons together in what will be called a neural network. So we'll inshallah study neural networks. And if we have time, inshallah, we will also study efficient ways of this feature mapping called kernels. Inshallah, both will be in the second half of the course. But keep that in mind, that perceptron by itself, it's good, but it's only for linearly separable data sets. Okay, so if it's not linearly separable, it will not converge. It might give you something that is good enough, but it will not converge. Okay, so that's the biggest limitation of Perceptron. Any question about Perceptron before we switch to a new session? Yes. Is there what? No. In some problems now, especially dealing with text data, we have millions of features. For images and videos, millions of features. So the number of features is easily getting much larger over time. So there's no limit. In theory, of course. In practice, you have to limit, of course, right? Because we are working with computations, right? With computers. So you have to have some limit. But in theory, there is no limit. In the new session, we will not learn a new model, but we'll learn so many important points about how to actually use machine learning in practice. Okay, there are many issues that we need to discuss in order, inshallah, to have a successful machine learning application. Right. So we'll cover how to deal with features, how to evaluate models, cross-validation, which is another way of tuning or reporting the evaluation of the performance of the model, statistical significance, and how to debug your model to see where exactly the problem is. We'll also cover the difference between estimation and approximation error at the end of this session, inshallah. But we will start with where machine learning application, or where machine learning is positioned within a real world problem. And if I have a real world problem, where is learning exactly? And is what we discussed everything that we should care about in a real world problem, or it's just one step? So for that, we will have an example, a real world example, which is discussed in the textbook also. The example that we will, inshallah, discuss today is that we have, let's say that we have a search engine company, and we want to increase the income for that company. Okay? And we thought that one way to increase the income or increase the revenue is by displaying ads, displaying better ads actually. Okay? So we assume that we have already a way or mechanism for displaying ads. You know the ads, right? When you search on the left, you get some results, and on the right, you get some ads, right? So we want to have a mechanism or a way to improve the displayed ads. Okay? Type. How is that related to the revenue or the income? Do you know the business model here? When you search, you get the results, right? You get the ads. If you click on any of these ads, what will happen? Huh? You will go to the advertiser, right? Website. But with that, the advertiser will pay the search engine, because the search engine managed to convince the user to go to that website. Okay? So any click on the ads will generate revenue for the search engine company itself. Right? And that's logical, right? Okay, so that's the model. Now we want to improve to get more revenue. If you as a user, you type the query, let's say that you want to book a flight. Okay? And when you typed booking a flight to Amsterdam, مثلا, and then you got ads about restaurants, will you click on any of these? If you are hungry, maybe, but usually you will not, right? Because that's not relevant to the query that you are searching, right? It's not relevant to the topic that you are interested in now. So there is mismatch between the ad and the query in this case. So as long as the ads and the query are relevant to each other, then there is a possibility that the user will click on this ad, and thus the company will get more revenues. Okay? Now, what you see on this slide is the steps that if we are trying to address this problem, the steps that we will take. So the first one is to determine the real-world goal. So on the left here, you will find the general steps, and on the right, the specific step for this specific real-world problem. So the real-world goal is to increase the revenue, as we said. The mechanism by which we want to increase the revenue is to display better ads. Now, how can we convert this into a machine learning problem? Because we are talking about machine learning here, right? So how can we convert this into a machine learning problem? One way is to think about clicking on the ads as a classification problem. How is that? I want to build a classifier. I am a machine learning designer now, okay? I want to build a classifier that will tell me if the user, or will guess if the user will click on that ad or not, given the query. And given a query and given an ad that I want to display, I want the classifier to tell me, will the user actually click on this or not? Because if the user will click on that, then what should I do? Then I should display this ad, right? And if there is a big chance or high chance that the user will click on this ad, then I should display it. If the classifier tells me that no, there is very low chance, very low probability that this user, this ad will be clicked with this query, then I shouldn't display it. And if I have good classifier that does this, then this will allow me to display better ads and thus maybe get better revenue. Okay, so you got the idea now? So this is now formalizing or converting the problem into a machine learning problem. Do you see the machine learning problem now? So now we want to build the classifier. What will be the input to that classifier? What is the input? The ad only and the query. Both the query and the ad, right? The query that the user will write and the ad that I want to check whether I should display or not. Okay? And what should be the output of the classifier? Yes, true, false, right? Binary decision. Should will the user click on that or not? Right? So this is what we call classify or click through, whether the user will click on that ad or not. Because if the user will click on that, then I will get revenue. Okay? Right. So this is now just defining the learning problem. Next, I need to in order to build that classifier, I need to collect the data, right? It's just now in theory. This is the problem, and this is the how I will address the problem, and this is now the machine learning problem. Did we do anything yet? No. So we need to train the classifier, right? How do we train the classifier? What do we need to train the classifier? Training data. We need training data, right? So we'll have to collect training data. Type. How can we collect the training data? We are a search company, right? We are displaying some ads now, right? And we log the interaction from the users. Whenever the user clicks on a link, we log it, we store it. Whenever the user click on an ad, we also store it. Okay? So we can make use of this data. So from the interaction of the current system, we can collect the data that will help us. So if the user wrote a query, and let's say the query that we just mentioned, booking a flight, and then an ad about a restaurant came, and the user didn't click on that, we will store that. Okay, we know that maybe this is now a negative example, right? If I got Qatar Airways ad, then it will be positive example. And of course, assuming that the user clicked actually on this link, on this ad, then it will be positive example. So this is the kind of data that we will collect from the interaction with the current system. Now, the collected data, as we mentioned, will be the query, the ad, and whether the user, and the click, right? Whether the user clicked or not. What's the next step? So this is now I understand what should be collected, right? طيب, let's assume that we collected the data already. We have it already in the current system. طيب. This is raw data, right? We have the query, like booking a flight to Amsterdam, and we have the ad, Qatar Airways, and we have +1. طيب. What is the next step? We need to represent the data in order to run the learning algorithm, right? For example, for KNN, we need numbers, right? So we have to have feature vector for each example. How can we get the feature vector in this case? We have text, right? The query is text, the ad is text, right? So we have to convert that into a feature vector. Right. Now we'll stop this example and talk about how we can convert text into a feature vector. Let's say that we have this booking. This is a query, right? Booking a flight to Amsterdam. Okay. Okay. So that's the query. How can we represent it actually as a feature vector? Usually, here's what we do with textual data. Let's say that each possible word will be a feature. How many words in English? Maybe 10,000? Let's assume that there are 10,000. Okay? So we will assume that we have a feature for every word. So we'll have a feature for the word A, which is the first feature, up to maybe the word zoo, which is feature number 10,000. Okay? That's the number of possible features. Now for this query, each word here appeared already, right? In the query, right? So it has one of these features, right? So the word A appeared here. So we'll put 1 for representing this query. And we'll find where is booking. Let's say booking is here. So we'll put 1 here. Oh, sorry. Actually, we write. So booking is here. We'll put 1 here. Amsterdam is here. We'll put 1 here. 2 is somewhere here, and maybe flight also. So flight will have 1. Sorry? Because we are now representing all possible words. Okay? But we will only put ones in the dimensions that have the words that are in the query. So we have 1, 2, 3, 4, 5 words, right? So we'll have 5 ones. And for all other features, we will have zeros. This is now a feature vector representing this query. This feature vector has how many dimensions? How many dimensions we have here? How many dimensions? 10,000. 10,000 dimensions. Okay? How many ones we have in this vector? Only 5. Why? Because we have 5 words. So there will be 1 in the dimension that is representing each of these words. Okay? This representation is called bag of words. Bag of words representation. Why is it called bag of words? First, it has words, of course, right? So we have the words. But why is it bag of words? Imagine that you got this query as words and you throw the words into a bag. What will happen? What will happen about the order of them? It's gone, right? It's gone. So here also the order of the original words in the query or in the text in general is gone. That's why it's called bag of words. Now we don't know the order. We don't care about the order. Okay, we just care about which words appeared in the text. So this is a general representation for any text data. So we can represent the query this way, and we can also represent the add this way also, right? Because the add is text also. So both the query and the add are text, right? Right? So for the query and add to be one example, how many dimensions we will have? We'll have 10,000 for the query and 10,000 for the add. So the feature vector will be 20,000 dimensions in this case. How many ones we will have? Very few, right? Very few. Even if we have very large document, by the way, any very large text, okay, we will have very few ones because it will not have all the words in English, right? So this is called a sparse representation. Sparse means most of it is 0 and very few are ones. But this is a very common, very well, commonly used representation for text. Okay, actually, that's the most commonly used representation. Okay, we'll have to stop here. Do you have any questions? Yes.
What if we have repeated words?
Good question. We'll answer it next time. Any other questions? But for now, let's assume that even if they appeared multiple times, it will be just one. Okay. Any other questions? Right. Inshallah, see you next lecture.